Hello and welcome to the supplemental lecture on torque and angular momentum. The reason we're highlighting torque and angular momentum today is because they are great applications of the vector multiplication called the cross product, also called the vector product. And that's going to be the mathematical focus, and then the physical concept is going to be applying it to torque and angular momentum, both rotational quantities. The key idea is that the cross product is a way to multiply vectors where the product is itself a vector, which is distinct from a dot product, okay, where the product was a scalar. And when did we see a dot product before? We saw it with work, specifically work by a by a variable force, all right, or a varying force. But here we're talking about torque because it highlights the cross product, well, and angular momentum. But first, torque. All right, so let's take a look. So we want to calculate torque magnitude and direction from the cross product of displacement and force vectors. All right. So perhaps we're used to torque being expressed as R times F times sine of the angle between the two vectors, where phi is the angle between R and F. And that's the magnitude of torque. And that implies that it is a cross product because it tells you that the maximum magnitude is when the angle is 90 degrees. And that is consistent with what we see with the cross product. Because one application of the cross product is when you have two vectors in a plane, such as the xy plane, when you have vectors like this, then their cross, the vector that they produce when they are multiplied together to produce a vector, or cross product as opposed to a dot product, but the result of that multiplication is a vector that is perpendicular to both vectors, thus perpendicular to the plane that the two vectors are in. All right? So this could be tau, this could be r, and this could be f. All right? And so that's one of the key ideas, is that cross products are largest when the angle between them is 90 degrees, okay? Although the focus here is mostly just going to be how to actually do the cross product and get the vector in vector form. All right, well, I'll finally get to it, okay? So here we have our one key formula, our physics formula, okay? It's got the torque vector, so tau for torque. We have the displacement vector, r, and we have the force vector, f. Probably the thing that might be the most immediately confusing is the displacement vector, if you don't recall how torque works, namely that torque makes no physical sense if there isn't a displacement vector. The displacement vector sometimes is the moment arm, other times it is a component of the moment arm, or rather the moment arm is a component of the displacement vector. But what it is, it's the idea that rotational terms like moment of inertia or angular momentum, which we'll see in the second half of this lecture, only make sense if they are defined relative to some pivot. And if you have some displacement relative to that pivot or axis of rotation, that is your displacement vector. Okay, so that's the idea. All right, so that could be, if it's a wheel, that would be the axle that the wheel is attached to. That would be the distance from that rotation point, from that pivot point, from that axle would be the displacement vector. Okay, otherwise there's no way to define torque. Okay, all right, so there it is, the cross product. And there is the notation for the vector cross product. And we'll talk about how to do it in just a second. First of all, I want to make sure that we're clear on unit vector notation. You may have seen this before, okay? Oh, and this is just showing what a vector might look like, all right? And this is definitely a prelude to the unit vector notation. So this is some vector like the displacement vector, for example, r, and I would define it in terms of components, x, y, and z components, and then all multiplied by unit vectors. So the result is, of course, a vector, okay? But what is a unit vector? And what is unit vector notation? Well, a unit vector is a vector of magnitude 1 that points along one of the coordinate axes. All right. The names of these unit vectors are I hat, j hat, and k hat. All right. So we'd say it like j hat and so on. K, k hat, I hat. I hat is along the x-axis, j hat is along the y-axis, and k hat is along the z-axis. All right. And so they look like this. The reason that they're length 1 is so that we can multiply a component of a vector by them, and then their only purpose is to make sure that that component points where we need it to along the x-axis without changing its magnitude. Because if we multiplied by some other vector, something that didn't have length 1, then we'd actually be affecting the vector, which we don't want to, because we want to preserve the original vector, but express it in a handy notation. Okay? There are other ways to express the vectors, but this is the only notation that we'll use for expressing vectors in this class. All right? So here we have an x, y, and z coordinate system, what is called a right-hand coordinate system, with x here, y, kind of basically like a typical x and y coordinate system or Cartesian plane, and then z coming out of the page, kind of drawn here in perspective. All right? Okay, so hopefully we're clear there. That's just the notation. All right, so now let's get to how you actually carry out a cross product. Okay, so it's vector multiplication that produces a new vector, not a scalar. This is what it looks like, okay? And I'll use the example of R and F. All right, so we look here, we zoom down, and we see I put this notation here. This is called a 3x3 determinant. I'm not worried about that. That's definitely outside the scope of the class. What we care about is that this is a handy way of remembering how to associate the terms in the cross product. Because the cross product has more steps to it, or at least one larger immediate step than the dot product, okay? And it involves kind of how to group together the components. Notice I have some color coding here. I have pink, I have orange, and I have green, all right? So pink is going to be attached to the I hat, which is the X direction. Then we can see the green is going to be attached to the J hat, which is the Y direction. And then the orange is going to be attached to the K hat, which is the Z direction. And we'll see what I mean by attached in just a moment. All right. And so basically, whenever we do the cross product, we look at everything that's not in the column that has the actual direction that we care about to be attached. Okay. All right. So this is what it looks like, right? And I've underlined one of them. So we have attached to the I hat. So in other words, this is the scalar or the component that is pointing along the X direction, right? Because this is a magnitude. This is just a scalar value, right? These are all scalars. They're just components, right? But we're multiplying them by a vector that's giving them direction, all right? And notice that what I did is I took ry times fz, that's this right here, and that's why I've kind of circled it in this elliptical format here, because I'm noting to myself that I have to multiply ry times fz in order to get that first term. Then I subtract the next term, which is just rz times fy, which is this circle here, okay? And then I know that it's ry fz minus rz fy, okay? Likewise, for the j hat, it would be rx times fz minus rz times fx. See? Rx fz, rz fx, okay? Now, right, and a minus between. But notice the j hat has something strange. It has a leading negative. The I hat term, the direction along the x-axis, had a positive in front, right, implied by there being no negative. And likewise, when we get to the k hat, or the z direction, we'll see that it's also positive. So the only one is the negative. The j hat component, the y component, is the odd one out. But that kind of makes sense because it's the one that's split. It's the only one where that multiplication, kind of memorization method of doing the cross product is actually split along a column. All the other ones are grouped together. Because we see, look, with k hat, it's the same. We group them together, rx times fy minus ry times fx, like so, okay? And that's the cross product. That's it. And it's a vector, obviously. But it has, coefficients attached to each, or components attached to each of the directions, x, y, and z, respectively, okay? And that's it. That is your vector. That will tell you exactly where it points. All right, it'll be consistent with what I said. If you have a vector that is, say like your r vector is entirely along the x-axis and your f vector is entirely along the z-axis, then the cross you'll find, this is test this for yourself, you'll find that then it will point, the cross between them will point entirely along the z-axis, okay? Or excuse me, the y-axis in that case, because I said r was x and f was z. So in that case, their cross would point along the y-axis, perpendicular to both axes. Furthermore, the order matters, and that's so important. So because you can't just be like, oh, I remember that torque is the cross product between displacement and force. Well, but which one comes first? Because if I put F cross R, I will get a different value. In fact, I would get negative torque. So switching the order of the cross product, I won't prove it here, puts a negative on the vector that you actually get, which would be the wrong answer. All right, it'd be 180 degrees off from the actual answer. All right, so the order is very important. Now, how do you kind of get an idea of where the vector might point? That's mostly helpful for checking your work because you can follow this through and just get a result, but then you want to make sure that result makes sense. And to make sure that your result makes sense, or for simple cases where maybe you care more about the direction than the actual value, then you use what's called the right-hand rule. And this is so helpful. It takes a little bit of getting used to. The idea is that you hold your index finger to represent the first vector that you are crossing, the leading vector that's being crossed. That's your A vector. So that's represented by your index finger. Then you take your middle finger and you hold it at 90 degrees to your index finger to represent that these two vectors are at 90 degrees to each other. Now, are they necessarily at 90 degrees to each other? No, but the only parts that will actually survive, quote unquote, the cross product are the perpendicular components, which we know from the magnitude because we multiply the magnitudes together, r and f, and then sine of phi. Well, that's explicitly telling us that only the components that are perpendicular to each other actually survive the multiplication. Because in other words, another way we could write this is r perpendicular f, or we could write it as r f perpendicular, right? Where perpendicular is perpendicular to the other vector. So by very nature, it makes sense to hold the fingers at right angles to each other to imply that that's the actual parts of the vector that are able to take a cross product. In other words, if A and B are parallel to each other, then there's no sense in even using the right-hand rule because the cross product will just give you 0. So there's no even need to think about the direction because there is no direction because there's no vector. Okay, but now if there is at least some component of the vectors that's perpendicular, then you put A, the first vector that's being crossed, B, the second vector is being crossed. You hold your right hand, can't be your left hand, has to be your right, and then your thumb will naturally point in the direction of the cross product. Won't give you the magnitude or anything, but it will give you the direction right there. That's the right hand rule. And in this case, R would be the A vector, F would be the B vector, and tau would be A cross B. All right? So that's the right hand rule. I'll bring it up again when we talk about angular momentum because we use it in angular momentum as well because angular momentum is a cross product. Okay? All right, well, I got one example to do that involves the cross product and torque. Let's take a look. So, suppose a position vector r of a particle with a mass of 0.2 kilograms is the following. Notice our r vector here. What do we notice about it? Well, first of all, it's three-dimensional, and that's what you're going to see in all the examples in the homework for this handout, for the supplemental lecture. So, three-dimensional, it's got an I, a j, and a k hat component, all right? An x, y, and z component. It also is a function, right? So in other words, the displacement vector here is not a constant value. It is a function of time. And that makes sense. We're talking about kinematics essentially, okay? So we have that we have a linear change in the position along the x-axis. We've got parabolic behavior along the y-axis, and then we've got linear again and along the z-axis, all right? So it's a particle that's kind of moving in three-dimensional space following this particular function. All right, the position vector is measured relative to the origin, all right? Okay, that's good to specify. That's essentially our pivot point. And the movement begins at t equals 0, right? So that would be the original position is at t equals 0. And the only thing that would be non-zero would be that 4j hat component. What is torque about the origin? And then draw torque at a particular time, 2 seconds. Okay, so how do we go about doing this? First of all, it's good to visualize this. And I include, the x, y, z coordinate axes and all the examples and homework problems. So I have x and y and z. All right, here's negative z. And here's the trajectory. And we can reason out that this is what it's going to look like because we got a negative parabola along the y-axis, so it's kind of curving downwards. And then it's moving out in a linear direction along x and z. So it's kind of growing along this plane as denoted by the dotted red line, but it's also curving down parabolically in terms of its y position. Right? So that's its three-dimensional trajectory. Kind of interesting to visualize, but can be tricky, I get it. Okay? So first of all, we're going to use the definition here, r cross f. Now, we weren't given f, were we? But we know from Newton's law, right, the translational acceleration version of Newton's second law, that f equals ma. Okay? All right, so can we find a? Well, sure we can. Well, because we know that v is just the first derivative of our position function. So v is the derivative of r, the first time derivative, so d over dt. And that's all I do here is I just take the d over dt, the actual operator of the derivative, and I'm just going to take the derivative of this, well, time-dependent position function. All right, pretty straightforward because it's a polynomial. All right, so then my 5t just becomes 5. Over here, my negative 1.2t plus 4 just becomes negative 2.4 because the 4, well, you take the derivative of a constant at 0, right? And over here, my 4t just becomes 4. Pretty straightforward. And we need to do it one more time to get acceleration. So go ahead and take the acceleration as the first time derivative of velocity. And well, that's going to be even easier because this constant, so they go away when I take the derivative. And this one here is just going to become negative 2.4. All right. So that means I actually have a constant acceleration in the j hat direction. And that makes sense after all, doesn't it, right? Because x and z were linear motion. You can't have linear motion if there's an acceleration, right? That means constant velocity. Furthermore, this one was parabolic. Well, parabolic, think the kinematic equations, that denotes constant acceleration. And indeed, we see constant acceleration, and we see it in the axis we'd expect it. Okay? So that means we did our derivatives correctly, right? It's consistent with our understanding of the concepts. Okay, so now we can actually, now we're set up to do the actual cross product because we needed A to do the cross product. All right, and so here we have it. I write it in the form of the 3x3 determinant, again, just to help me kind of keep track of everything. I pull out the m because I can pull constants out front, even if they're on the second term. Okay, and then I'm just going to go through and think about what the cross product is going to be. So I'm going to say, okay, well, what's going to be attached to the I hat direction? Well, that's going to be this term times this term, which is going to be 0, obviously. And then these two multiply together, they'll be non-zero. And then in the j hat direction, I'm going to have, oh, that's just going to be all zeros, right? See, look, because 5t times 0 and then 4t times 0. So nothing in the j hat is going to survive. And over here, I'm going to have another 0 term, or a non-zero term, and one 0 term. See? Okay? So this is what we get. We have 0 minus 4t times negative 2.4 in the I hat direction. Right? Notice that there are functions within the cross product. That's totally fine. That just means that our torque potentially is itself going to be a function of time. Okay? And then we, like I said, the j hat is just all 0. And then, right? And then in the k hat, we have following our steps here, 5t times negative 2.4. So indeed, we are going to have a t by the looks of it. Clean things up a little bit. And there is our torque. Our torque is 0.2 kilograms times 9.2 t in the I hat direction minus 12t in the k hat direction. Okay? So what is that telling us? Well, it's telling us that our torque points, what way does it point? Okay? And does it point in a direction that makes sense? Right? Because it's basically pointing in the positive x direction and it's pointing in the negative z direction. So it's so if we think about it, and it's growing linearly, so the torque is non-constant, but it always has the same direction, right? And so it's going to be pointing somewhere like this. This is going to be kind of our torque vector, and I'll add it in, in just a minute. But this is where the torque vector is going to point. Does that make sense? Well, if you do the cross product, it actually does make sense, because another way you can kind of simplify the cross product, if you have a trajectory, and you want to just think about your thumb pointing in the direction of torque, you can curl your fingers along the trajectory. Now this gives you a perfectly accurate result if it's a circular trajectory, but here it's not, it's parabolic. But still, it's going to give you an estimate of where torque is going to point. So if I curl my fingers along that trajectory, and I kind of imagine, that trajectory kind of coming out, so maybe I move my arm somewhere, so I kind of curl my fingers along that 3D trajectory, then I see my thumb has to point back into the page, right? And it points into the page and off to the right. Indeed, just like our result tells us. Okay? So good. All right. And then I'm going to go ahead and factor in the 0.2, give everything the correct units because the units of torque are Newton meters. And there we have our answer. We have our torque vector about the origin. Okay, it's a time dependent vector. In other words, it's a function of t. All right, and then let's find it at a particular value at t equals 2 seconds. All right, so if I plug in 2 for both the t values, then here is my particular torque vector. All right, and then we want to draw it. All right, so here I basically just say to draw it, but I also report it. I think it's a good idea to report the value as well as draw it. And so let's draw after 2 seconds, and so it's going to be up here. There it is. Okay. So it's in the xz plane with a positive x component and a negative z component. See? All right, so that's it. And we took the cross product and we did some kinematics to make sure that we went from a position function to an acceleration function so we could actually take the cross product. All right, there we have the example with torque and our introduction to some ideas. All right, for the homework, you're gonna do it again. Really, no significant difference here, just a different position function, but all the same steps. I just want you to repeat the steps, okay? Now, second topic here is going to be angular momentum. I don't have as much to say about angular momentum because it is very comparable to torque. We're just crossing different vectors, okay? Now, because angular momentum is a cross product, but instead of crossing position with force, it's crossing position with translational momentum, all right? And so that gives us the units that we need, or which should be units of joule seconds. You should remember that from angular momentum. It is totally consistent with the idea what angular momentum represents, which is a quantity that's conserved. There's no external torques. It represents the idea of a rotating object or a spinning object that possesses this quantity if it's in motion, but doesn't possess it if it's at rest, which is unlike inertia, which you can possess even when you're at rest. So it's just like translational momentum, except it's angular momentum. But it's also a cross product, which makes it comparable to torque, right? And it makes sense that it would have a position because just like all angular terms, they don't make sense unless they're relative to some pivot point, right? Some origin, right? But instead of force, it's momentum, okay? All right, so there we have it. And of course, angular momentum is L. All right, so angular momentum is a cross product of position and translational momentum. And since translational momentum, P, is mv, we can pull out the m. So then we can always express the angular momentum vector with its cross product definition as m multiplied by the cross product of the position vector and the translational velocity vector, okay? Furthermore, we have the Newton's second law in angular momentum form. Compare this to Newton's second law in translational momentum form that says that F equals dp over dt, see, okay? But here it's tau for torque, and it's a net torque, which it was net force as well, is going to be dl over dt, okay? So that is just Newton's second law. How do we know it's Newton's second law? Well, let me show you, okay? So I'll get back to that in a second. So this is Newton's second law, all right? And so we could rewrite this as torque equals dl over dt, just drop the vectors for a minute, just to show that it is indeed Newton's second law. Express L as I omega, all right? That is only for solid rotating objects, but it'll serve our purposes, okay? Again, it wouldn't work for a translating particle, but I just want to show that indeed this is going to give us the result we'd expect for Newton's second law. So then we have the first time derivative of I omega. Well, we're going to assume that I, which is the moment of inertia, is a constant. It is not time dependent. In which case, which it can be time dependent, but if we assume it's not, because again it's a solid rotating object, then we just left with the first time derivative of omega. So just d omega over dt, which by definition is alpha, or angular acceleration. So there we have I alpha, and hopefully you recognize that, because tau equals I alpha is Newton's second law in angular acceleration form, which is so similar to F equals ma, right? So indeed, it's it's all the different ways. It's the 4 different ways of showing Newton's second law: in translational acceleration form, in translational momentum form, in angular acceleration form, and then finally this way in angular momentum form. But they're all Newton's second law. They're all totally consistent. And it's so I think I really bring that up and I stress it right now because it really does show how all these ideas are related to each other, and they're all very, very closely related. Often you can use a technique like an acceleration technique to solve a problem, or you can use a momentum technique, okay? Neither one's wrong, just one might get you there faster. But back to the idea of the cross product, okay? So since angular momentum is the cross product between the displacement vector and the translational momentum vector, then we have R cross P equals L, right? So I'd hold my index finger for R, my middle finger for P, and then my thumb points in the direction of L, okay? So that'll always reassure you on the direction that L should point. All right. So I kind of have a similar type example here that we saw for torque, but this time the focus is angular momentum. Okay, so suppose the position vector r is in the xz plane and is given by this function right here. So here we have a position function. This time it's not time dependent, okay? It's just a position function, all right? It's just maybe it's at a particular moment, but it itself is not a time dependent position function, okay? But it's still the same sort of setup. And it's in the xz plane, but we know it's in the xz plane if we just look at the vector, so it's redundant information. And part A, what is the angular momentum about the origin of a particle moving with translational momentum negative 10t I hat, okay? And then there's the units of translational momentum, which are Newton seconds, as compared to the units of angular momentum, which are Joule seconds, okay? So essentially, that means that we have some, position vector and the particle's in motion at that moment in time, and this is kind of its bearing, right? That's the direction of its velocity vector at that moment in time. Because after all, P just equals mv as vectors. In other words, translational momentum is always parallel to translational velocity, okay? So what that would look like is this, okay? So here is the position vector relative to the origin, and there's the momentum at that moment in time, okay? So that's our information that we have, okay? We have the position and the momentum at that moment in time, okay? Now the momentum is changing, okay? The position is not, okay? So we have a position that is kind of, fixed in place, but we have the idea that we have a time-dependent velocity, okay? All right, so then we're gonna draw the angular momentum after a certain number of seconds, okay? And then that's gonna be the end of part A, and then in part B, we're actually gonna relate it back to torque, because after all, there's a direct relationship between torque and angular momentum, as highlighted here by this Newton's second law, this version of Newton's second law. Okay, so first the cross product, same idea, write it out, use our determinant here as a handy-dandy way of remembering how to associate all the terms. And so if we look at I hat, that's just gonna be 0 times 0, minus 1.4 times 0, so all zeros over there. On the j hat, we've got a 0 term, because that one's 0, right? But then this one will survive, because 1.4 times negative 10 is gonna make it through. But on k hat, it's gonna be all zeros again, because 1.2 times 0, and then 0 times negative 10t, okay? So it means the only direction that's non-zero is the j hat, or y direction, and it ends up being negative 14, okay? Why negative? Well, because we have a negative, and a negative. Right, so a negative times a negative is a negative, okay? So there we got it, negative 14t. So we have a time-dependent angular momentum, just like we had a time-dependent translational momentum, okay? So at 4 seconds, there is our value, negative 56 joule seconds in the j hat direction. It's a vector, and at this point, you know, that's its value at that particular moment in time. Okay, looks good. And if you kind of think like, how could you have a time-dependent, velocity, and a fixed position? Obviously, this particle isn't moving exactly, right? There's no real, trajectory here. It's just kind of it's maybe more like it's different snapshots in time, or maybe it's different particles that that we're comparing, between their times. But regardless, I decided to keep it simple and just have that. Now, I suppose we could have done things differently. I could have had you go the same direction and take the derivative of position to get the velocity and go from there, right? So you definitely could have had a velocity that was directly tied into this position function. In that case, I would have given you a time-dependent position function. But let's not worry about that, right? We're still following all the steps, even if it is a little odd to have a constant position function and a time-dependent velocity. All right, just let's accept it for what it is. We can still solve the problem. Okay, and maybe you weren't even concerned about that. Anyway, so I have here some color coding. I want to show that the angular momentum vector is this vector right here, and this is a great opportunity to check it with the cross product, right? With the right-hand rule, that is, right? So take your index finger and pointing the direction of R, kind of out of the page towards you, and then use your middle finger to point towards your left. And then you'll find that, okay, so if we do this, yep, if you do that, then you'll find you have to kind of turn your arm awkwardly, but you'll find that your thumb has to point downwards, okay? There's no other way to make that work. And you might say, okay, wait, but how am I going to do this? Well, just take the component of R that's perpendicular to P. So I would just take R perpendicular and then take P and then cross those two, okay? And that will give you L, which has to point down, okay? But anyway, there's your value. Let's move on to point B. So on point B, all I'm going to do is take the derivative of the time derivative of angular momentum. So if I have a angular momentum which is linear, then I should have a torque which is constant, right? Because when I take the derivative of this, it just becomes negative 14, all right? Units of Newton meters. Excellent, okay? So then that means that this vector has to be parallel to torque, but it's going to be, it's got different units, not necessarily longer, because you might say, oh, 4t is shorter than 56, but these are totally different units, so it doesn't really matter, how I draw them. I just want to make torque visible, so I drew it longer, so it'd be, visible on the page, but it's parallel to angular momentum. Okay, now, torque isn't always parallel to angular momentum, but it is always parallel to the change in angular momentum, okay? Because we see that torque always points parallel to dl over dt, okay? But in this case, because angular momentum was just pointing in a single direction, it was unidirectional, right? It didn't have any other components other than a j hat component. That's why torque is parallel to L. But that's not always the case. All right. So that wraps up this lecture, highlighting the physics application of the cross product in rotational systems, specifically for torque and angular momentum. I hope it has been interesting and informative, and I hope the homework problems go smoothly. They are, as if you look at the second homework problem for the second section, that they are very much comparable to the examples. They're just a variation on a theme. Okay? All right, bye for now.